Okay, perfect. I will then continue. So, maybe briefly recall the main takeaway from what we did so far. From lambda, we obtained for so setting y to the derivative of z for some complex number z and x to value of z, an equation which looks very much like an elliptic curve. So, well, we agreed at some point that our standard form for an elliptic curve always has a 1 here and some pluses here. This is no issue because replacing in this form x and y by x over 4 and y over 4, you obtain the usual Weierstrass form. So this is just another form which is a bit more useful for our case because it's precisely the differential equation of the Weierstrass p function. And this is elliptic, so an elliptic curve now is, maybe make this precise, an elliptic curve if its discriminant does not vanish, and its discriminant, one can show this from what I just said, is just g2 to the cube minus 27g3 squared. So if this is non-zero. So this is now the usual discriminant of an elliptic curve computed via the coordinate transformation. So we have to show this, that this always holds for our lattices, or to give at least some restriction when it holds. But yeah, the main takeaway is it holds always. So for a lemma, so we are now going to prove this, and we need a lemma. So every point which is not a lattice point is 0 of the derivative of the Weierstrass p function if and only if 2 times this point is in lambda. So note, this leaves us with well, precisely 3 points in any fundamental domain, namely the two half the two generators and half their sum. So yeah, there are in the book I'm following, there are a bit more theorems like this, because they also prove the addition. There's an addition formula for the Weierstrass p function, which is basically, well, which can be used to define the addition on an elliptic curve, but it is just annoying to write it down, and we don't need it anyway. But there are a lot more of these kind of theorems that, if you consider particular sums and differences and stuff, that you can derive such conditions. But yeah, anyway, this one is particularly easy to prove. So first off, I claim any such point satisfies this, and this is a simple consequence of the periodicity of the derivative of the Weierstrass p function and the fact that this is an odd function, because assuming 2z is a lattice, not a lattice point, well, is a lattice point and z is not, then this gives you this equation by just subtracting 2z, and this here is, as the function is odd, just minus of this value, so meaning this has to be 0. So any point satisfying this condition is actually 0, and now I claim that these are all the points, and this is actually pretty simple, because we have these powerful characterizations of elliptic functions. So letting omega 1, omega 2, and omega 3 be these values. So these are just the generators of our lattice, and this is their sum. So in the end, if you have this fundamental lattice, these are precisely these points. And taking their halves gives you these points. We know that half these values, so omega I over 2, is 0 for I equal to 1, 2, and 3. Simply because these are not lattice points by construction, and two times these points are lattice points. But now we have to recall the following result. We had Liouville's third theorem, which tells us that the number of the number of poles and the number of zeros in any fundamental domain is equal. But we know by construction that this here is an elliptic function of order 3, meaning it has 3 poles in any fundamental domain, and these are 3 zeros in a fundamental domain. So these are necessarily all the zeros. So meaning the reverse simply holds because we can classify all the zeros. So you will 2 all zeros. And they obviously satisfy the condition I placed on them. Okay, this for lemma. And we are now going to use this lemma to prove another lemma, which is that the discriminant of the elliptic curve defined above is always non-zero. Okay. Okay, so what are we going to need to prove for this? We know that this discriminant here is just a scalar multiple of the usual discriminant of this polynomial. So meaning what we actually have to do in the end is we only have to consider the zeros of this polynomial and show that they are all distinct. And by this lemma here, we know this equation here becomes 0. So let's call a star. Star is 0 equal to 2x minus g3 if and only if we evaluate this expression at these omega I halves. So what we have to show is, well, we know that these are then all the 3 zeros of this equation, and we have to show that the values of the Weierstrass-B function at these values are all distinct. And again, we do this by appealing to one of the Liouville theorems. So define fi of z as the Weierstrass-B function of z minus the Weierstrass-B function valuated at one of these points. So this function here is, consider this for 1, 2, 3. We actually only need it for 1, but anyway. This here is elliptic of order 2. Simply because the Weierstrass-B function is elliptic of order 2. And we know, first, we know fi of omega I over 2 is 0 by construction. But we also know fi prime of omega I over 2, which is just the derivative at omega I over 2, is also 0. Meaning, in the point omega I over 2, this function has a 0 of order 2. However, this function is also elliptic of order 2. Meaning, these are all the zeros. And these zeros are in particular all of order 2, meaning there are no other zeros. In particular, evaluating these functions, so yeah, maybe write this down. 0 of order 2, and thirdly reveal all the zeros. In particular, we get that omega these values do not agree if I is not equal to j. Okay, so this proves that all the zeros of this equation here are distinct, and this in the end just gives us precisely that the discriminant cannot vanish. Okay, so, and to maybe briefly close this chapter, what we did so far, what we did associate to any lattice an elliptic curve using the Weierstrass-B function of this, the Weierstrass-B function of this lattice. Yeah, that's readable. Okay. What we now have to show is somewhat that over C, any elliptic function arises in this way. So meaning, whenever we are given an elliptic curve with some arbitrary coefficients g2 and g3, such that the discriminant does not vanish, we can find a lattice with precisely these invariants, or say at least up to some scalar invariants. And that's what we're going to do now, and I will now be a bit more precise with respect to this scalar invariance. So what we actually want to show in the end is the set of elliptic curves up to isomorphism as defined in the first exercise sheet, so some scalar invariants of the coefficients, and one-to-one correspondence with lattices up to homothety. So what we want to show is up to homothety and isomorphism we can always find corresponding things. Okay, so this will be then the second part. So recall we had defined for elliptic curves a J invariant, and you showed on the first exercise sheet that the J invariant classifies an elliptic curve up to isomorphism. And well, we are now in the same situation. We can just do the same for a lattice. We can define to a lattice a J invariant, and what we are going to see is that this J invariant first has the same classifying property, meaning two lattices are homothetic if and only if their J invariants agree. But even more interesting, we can extend the J invariant to something called the J function, which then will be a holomorphic function on the upper half plane having some very interesting properties. And this allows us in the end to construct lattices with given discriminant, or with given coefficients. So yeah, so let's start with definition for lattice lambda let G. Yeah, okay. So as usual, our nice factor giving some normalization, and then G2 to the 3 over G2 to the 3 minus 27 G3 squared. So it's just G2 to the 3, 1, 7 to 8 over the discriminant of this lattice. That be its J invariant. Okay, now it becomes awful. Okay, so we know from the what we just proved that this is always well defined, and we are now going to first the theorem I promised. These J invariants classify lattices up to homothety, meaning for two lattices in C, the J invariants agree if and only if they are homothetic. Okay, so for the proof, the first part, the first direction of the proof is exactly the same as for the case of elliptic curves. So if the two, okay, maybe let me add a small remark before going into this. The J invariants of any multiple of our lattice, so the G2 and G3 of any multiple of our lattice are just scalar multiples of the original values, and this is completely clear from the definition of these constants, as they are just summing over all lattice points, and if we scale every lattice point up, you get just the scalar and to the power of the defining series. So we define G2 and G3 in terms of the Eisenstein series of, well, degree 4 and 6. So this is why there's a 4 and a 6. And now this then in the end gives us, okay, these things are homothetic in the end precisely when we can arrange the constants like this. So meaning precisely when the elliptic curves are isomorphic. So meaning by what we proved on sheet 1, I think it was, sheet 1, if the J invariants agree, lambda 1 and lambda 2 are homothetic. Okay. No, that's not what I wanted to prove. That is not what I want to write down, sorry. It's precisely the other way around, sorry. So if lambda 1, lambda 2 are Yes, sorry. Okay. This has nothing to do with sheet 1. Sorry. If they are homothetic, they have the same J invariance. Simply because these coefficients here, these powers of these coefficients get matched because this is homogeneous in G1 and G2. Well, not completely homogeneous, but with respect to these, if you plug in a 4 here, you get a 12, you get a 12 here, and if you plug in a 6 here, you get also the 12 power here, so they cancel each other out. So, sorry for that. So this is the trivial direction, and the backwards direction, in the end, relies on what I just told you. So now be more precise. If the J invariants agree, then, by a similar argument as we did on sheet 1, we find a non-zero lambda with these conditions. So this is now what you did on sheet 1, because this is precisely saying if two elliptic curves have the same J invariant, they are isomorphic as elliptic curves, and an isomorphism of elliptic curves is precisely this condition. Okay, now I'm back on track. Okay, and now I claim that, well, this lambda is precisely the scaling factor we need. And this follows from the following. For the scaled lattice, we have that the the values of the G2 and G3 agree. Well, simply by construction. So these agree, and hence, and that's the only reason why I needed this independence and the Lorentz series expansion of the Weierstrass-B function. This implies that all these coefficients agree, simply because these are rational polynomials in G2 and G3. So if G2 and G3 agree, all these things agree, and hence the Weierstrass-P function of these two lattices have to agree in the neighborhood of the origin, because that's why the Lorentz series is in the end happening, and then by the ellipticity of these curves, so by placing around the values, we actually conclude that these two have to agree everywhere. But this is, of course, only possible if the lattices agree, because by construction, the Weierstrass-P function has a pole of order 2 in precisely every lattice point. So if these functions agree everywhere, and in particular their poles have to agree, and their poles are just the lattice points. So yeah, and this is, as I think, a very neat proof of such an identity, by in the end reducing it to an assertion about complex functions. So yeah, this gives us the theorem. So this is the J invariant, and as we now know that the J invariant somewhat is all we need to understand in order to understand the elliptic curves, because if you now can just construct for any given value of a J invariant some lattice which had exactly this J invariant as its value, we are done. Precisely by this. We are done up to homotheity and up to isomorphism. And this is, again, this is in the end precisely what we are going to do. And for simplicity, what we do this by studying the so-called J function. So the J function is defined on the upper half plane. So all complex numbers with an imaginary part strictly bigger than 0. We define this J function simply by looking at the lattice a point generates. And as I remarked in the very beginning, this suffices to study all lattices up to homotheity. Because by as I mentioned there, we can arrange every lattice by rotating it a bit and scaling it a bit so that it is of this form. So it suffices to study the J function, and studying the J function only on the upper half plane is particularly, well, easy is not maybe not the right word, but it makes some arguments a bit easier. Okay. So lemma. What we now first are going to establish is that this function here has a huge amount of symmetries. Sorry, any question?
Yeah, just for the definition of the mapping. What is
This here? The upper half plane. So maybe let's write it down explicitly. These are the points which have imaginary part strictly bigger than 0. So only the upper half of the plane. Okay, thank you. Yes. So what we first are going to establish is that the J function has a vast amount of symmetries. And we first need these two. This is just translation on by 1, and this is inversion of the unit circle. Yes, so these two are immediate from this definition, because the lattice generated by tau and tau plus 1 are exactly the same. And similarly, if we have the lattice generated by 1 and minus 1 over tau, just plugging it out, just scaling this out. Well, okay, I can write it down, sorry. It gets a bit too confusing, I think, if I just say it in passing. This is simply due to this fact. So this one is obvious, and this is just by scaling the lattice appropriately. So, and in particular, because we know the J invariant of a lattice is invariant under homothety, this gives us that the values agree. Okay, so we have some amount of symmetries, and it becomes clear why I only pick these two in a second. So what I'm now going to prove is that the J invariant is injective if we divide out a particular action on the upper half plane, and what we want to divide out is the action of SL2Z. So maybe to make it discrete, these are discrete Möbius transformations. These are precisely discrete Möbius transformations because we only consider, so Möbius transformations are in general generated by considering translations, scaling stuff, and inversion at the unit circle. And well, the scaling stuff kind of falls apart if you only work on the upper half plane, because you can, well, the only way you can invertibly scale on the upper half plane is by just doing nothing, because multiplying this minus 1 might get you out of the upper half plane. So, and of course translations also only work in discrete steps, but inversion at the unit circle is still completely fine. So I will explain how this acts in a second. So this tells us that the J function, the only symmetries of the J function come from these discrete Möbius transformations. Okay. Okay, the proof is the following. So SL2Z acts via Möbius transformations, meaning if you have some integer matrix A, B, C, D, let's call it gamma, then gamma of tau is A tau plus B over C tau plus D. And you can check that this maps elements of the upper half plane into elements of the upper half plane. Yes?
I have a question to the intervals. So are these
These are not intervals. This is my notation for lattice. Yes, I explained like this in the beginning. So these are the two generators of the lattice. Okay. Okay, perfect. Yeah. I see, yeah. It was a while ago. Yeah, but just writing it down as Z multiples is a bit annoying for the time being. Okay. Good. So an integer matrix acts just by considering the associated Möbius transformation. So, and then the backwards direction is immediate from dilemma because noting two things. First off, inversion at a unit circle can be realized by considering this matrix. Simply because what you get plugging this in is -1 over tau. And similarly, you can realize translating by 1 using a matrix 1, 1, 0, 1. So yeah, 1, 1, 1, and 0. Okay. And now I will not prove this. It's, I think, not too hard to see especially from this, viewing this here as discrete Möbius transformations, it's kind of clear these two generate the whole group of SL2Z. Because, well, the Möbius transformations are generated by translations, inversion of the unit circle, and scaling. And when we are working on the upper half plane, these are the only two left which can do something useful, and they generate all the translations, and this is the inversion of the unit circle. So these generate SL2Z, and because we know the J function is invariant under these two, it is in fact invariant under the whole group of SL2Z. I'm too small. Okay, that's for the forward backwards direction, and the other way around is just the following. So assume J tau is equal to J tau prime. Then we know that by the theorem above, if the J invariants of two lattices agree, they are homothetic, meaning 1 tau prime is a scalar multiple of 1 tau, and of course the other way around with lambda inverse. And this gives us the following: lambda tau plus b lambda. So we can express tau and 1 as multiples of 1 lambda and lambda tau. So this is immediate from this definition. And well, considering the quotient of these expressions, because they are both non-zero, what we get immediately is that tau prime is the image of a Möbius. Oh, not yet. We not know that this is invertible, but we know at least that it looks right. So we have a scalar matrix A, B, C, D, which acts on tau to give tau prime. And doing the same thing the other way around with lambda inverse, so what we get from here is, so letting this be gamma, we get that tau prime is gamma tau, and similar, I hate this word, and similarly we get that tau is gamma prime times tau prime. Okay, we have these two expressions, and plugging them in one another, we can conclude that gamma is in fact invertible. So tau prime is gamma tau is gamma gamma prime tau prime. Hence, gamma is the determinant of gamma. Determinant of gamma is plus minus 1. And now, because both of them are on the upper half plane, the determinant has to be actually 1, because otherwise we would switch around. So this gives tau prime in the upper half plane is this one. So yeah, so this is actually an element of SL2Z. And we showed that these are all the symmetries. Okay, and now for the final part, which is again just applying almost every complex analysis you can think of to conclude. We will prove the following theorem. J is a holomorphic surjection. And this part here is what we are looking for. So, because then we know we can hit every, so giving any G2, G3, which define an elliptic curve, we can look at the J invariant of this elliptic curve, and using the surjectivity, so this will be just some complex number, and using the surjectivity, we can actually find a lattice in the upper half plane which maps to precisely this J invariant. So it defines us an isomorphic elliptic curve. Yeah, and what we are going to need for this, well, we don't need it in this form, but might as well mention it here. If you look at the complex plane again, you can also find a fundamental domain with respect to this action. And the usual choice is the following. You consider the strip of from -1/2 to 1/2 around 0. So you can first translate every point on the whole complex plane into this subset by using the invariance under t+1. And then you can go actually further. Where's 1/2? This is the unit ball. You can unit ball. You can get any point which is here out here by inverting at the unit point. So the only relevant stuff happens in here. So this is somewhat also this is very similar to the fundamental parallelogram for a lattice. So for the J function, we can reduce any question into this set here. So well, again, to get really a fundamental domain, this has something to do with uniqueness of representation. You have to get rid of some of the boundaries, but let's not care about this because we don't need it. Yeah, so this here is actually, this is, by the way, a third root of unity. And this is I. Yeah, never mind. Sorry. So, yeah, we can get everything in here. And the thing we want to note about this thing, it is, if we consider it with its boundary, this is a bounded set. And once we can somewhat bound when we consider particular stuff, we can bound the imaginary parts of our function, we get a compact set. This is now how we are going to prove the surjectivity part here. So yeah, this is somewhat the fundamental domain for the SL2Z action. Okay. That's that. And now for the proof. This will be the final preparation we need for the uniformization theorem. Again, start with a fact. GR. Oh no, that's not right. GR of tau. So tau now considered as the associated lattice is holomorphic for r bigger than 2. So yeah, as for the part absolute convergent, this is in the end not hard to show, but a bit tedious to write down, and I don't want to spend time on it. So hence J is holomorphic, simply because it is the composition of holomorphic functions. So, well, the numerator is holomorphic by this fact, and the denominator, which is just a discriminant, is also holomorphic by this fact. And as the denominator vanishes nowhere, we get a holomorphic function. So this is clear. So now for surjectivity, we call the following. We have the open mapping theorem, telling us the image of holomorphic function is always open. Well, if it's non-constant, is open. So we will see in a second that this is necessarily that this value is necessarily non-constant, but you can just plug in some numbers to see that you can achieve different values. You can, for example, achieve 0 and 1728. So you get at least 2 values, so it is non-constant. So this is open. It is non-constant, in particular also non-empty. But yeah, that should be clear. And what we now want to show is to show it JH is also closed. And as C is connected, showing that a proper subset, so some non-empty subset is both open and closed, necessarily concludes that it has to be the whole space. Yes, this is that. And my final stuff. And for this now we combine the symmetry observations with computation of some particular series. And so what we need to show is suppose we are given a series of points in, how do I write this here, in the image, which converges to some omega in C. Okay? We need to show that then we need some tau in the upper half plane with j tau is omega. So, and with all of generality, we can assume these tk, these tau k are all, so we log the series of the tk is completely contained in this fundamental domain. Just by, again, we are only interested in the convergence of the function values, and these are invariant under this action. So you can assume this, and okay. And now we only need one more theorem, namely, or one more claim, that the limit, well, okay, the other way around. We need that these are bounded, because as soon as we, yes, so we need that the values are bounded, because as soon as we know that these are bounded, it happens precisely what I told you here. As soon as we can bound these tk, we are left in some compact set. So then we can choose a converging subseries of this series, and by continuity, this converging subseries has to converge to the same point. So by taking the image. So we are only left with showing this, and to show this, we prove that the limit of the imaginary parts is going to infinity, that the j function also goes to infinity. And this then gives us the following. Suppose these values here are unbounded. If they are unbounded, they have to have a subsequence converging to infinity. But this is not possible, as we know that the function values actually converge. We know that the values actually converge to, where did I write it down? 2, yeah. Sorry? Thank you. Yeah, we know that they actually have to converge to some point within the complex plane. So they cannot go to infinity and converge to some fixed point, because at some point they have to be contained in a bounded subset. So this then gives us all we need. So we only need to prove this. And to prove this, well, I have to cheat a bit, because there's no time to really go into this, but we have the following observation. Taking the limit of the imaginary part going to infinity of g2 to r of the lattice tau, so again of the lattice 1 generated by 1 and tau, this we can write as, so this, remember, this is the sum over all the lattice points to the power of 2r. And we can split up this part here in a sum, say, of n, bigger than 1 over n to the 2r, plus some z, where n is non-zero, no, where m is non-zero, I need 1 over n plus m tau to the 2r. So we can just rearrange, we know these converge absolutely, so we can just split them up in these two parts. And well, this here always has some tau in it. So in absolute value, by going to letting the imaginary part of tau going to infinity, this part here goes to 0. And this part here, well, converges to, oh sorry, here should be a 2. 2 times zeta of 2r. Okay? So this is the Riemann zeta function. And I now have to somewhat black box this part. It's, I think, especially with the tools of complex analysis, it shouldn't be too hard to prove. I need the values of the zeta function at 2 points. And it somewhat becomes ridiculous at this point to prove, because what we are now going to see using this limit, the discriminant goes to 0 precisely because the coefficients of the g, smaller g, lower g, and lower g2, lower g3 match, so that this discriminant limit goes to 0. So yeah, let me, oops, that's the wrong one. Let me maybe write this down. So if you now, so yeah, from this we get that the limit for imaginary part to infinity of g2 tau, this is just 120 times the Eisenstein series for 4. So this is 120 and times, oh no, sorry, this is 60 times 2 of 4. And just believe very hard that this holds true. This is 4/3 p to the fourth. So these are just the values of the Riemann-Zeta function that even positive integers can be computed very explicitly using Bernoulli numbers in the end. And there are very clean proofs using complex analysis. Maybe we do this on the exercise sheet, I don't know. And the same, very similar thing shows that this is 130, 2 times zeta 6, and this is 8/27 p to the 6. Yep, similar argument. And putting this together, so imaginary part to infinity of the discriminant of tau gives us 4/3 p to the 4 cubed minus 27 8/27 p to the 6 squared. This is 0. Yes. Yeah, it becomes a bit ridiculous at this point, but okay. So, and because the j function is defined as something over the the point now is this converges hence to finite thing by taking its limit. This converges to 0, hence their quotient converges to infinity. This is exactly what we need there. So this proves the claim. And hence what we have is in TKK so the primum is bounded. Hence, pick converging subsequence. So by Lozano-Weierstrass, and this gives us the result then by the continuity of the j function, because we find a converging subsequence converging to some point in the complex plane, and the values of the images of these points necessarily have to converge to. We know the images of these, well, let me write it down. So what we get is the limit of, say, L to infinity of j of TKL, I guess. So this will be g of tau, where tau is the limit of this converging subsequence. And this has to be the same as the limit for the original series, simply because this is a converging subseries, and this converges to omega by assumption, and hence we found a preimage. And yeah, this proves this part. And I'm running out of time, but it might be good to actually give you the result I was working towards the whole time. And the proof now is. We already did all the necessary parts of the proof. So, but to state it now very explicitly, let's actually do the uniformization theorem. Uniformization theorem. Okay, and this is the following. We have one-to-one correspondence between elliptic curves over C curves up to isomorphism and lattices up to homothety. So this is the uniformization theorem. And to briefly argue how this works, we know how to, so we get from lattice an elliptic, sorry, that's not pig notation here. Lattice get an elliptic curve by using the Weierstrass P function and the associated differential equation. Another point is two lattices, so if we consider the elliptic curves up to isomorphism, we know we only consider the elliptic curves up to their J invariant, and we know then that two elliptic curves are isomorphic, precisely when their J invariants are equal. The J invariants are just the J invariants of the associated lattices, and hence the associated lattices are homothetic. So this is injective. So J variant injective, and the J function gives us the surjectivity because we know pick any G2, G3, so pick G2, G3 in C with non-zero. Then we can consider, well, the quotient, which just is the J invariant of this to be lattice. And we know by surjectivity of the J function, we find some lattice in the upper half plane mapping to precisely this value. So we find tau okay, now I've messed up somewhere. This way around? Ah, damn it. Yeah, something like this. So we find a tau which maps to precisely this value, and hence we know this thing here realizes the elliptic curve associated to these two complex numbers. And this then concludes the proof of the uniformization theorem. Yeah, exactly. Okay, maybe very briefly, I promise I won't go too much into detail, why this is useful. Well, what we now did is we translated an algebraic theory of elliptic curves into an analytic theory of lattices and associated meromorphic functions. And this is extremely useful simply because, well, the tools of the analytic theory are so much more powerful than the tools of the algebraic theory, whereas the algebraic theory is simpler to state and understand. And so this is a very particular instance of something which is called the Gaga theorems in algebraic geometry, which tell you that you can do this with a lot more stuff. So precise smooth projective varieties, you can always translate them into an analytic world and then use the analytic tools to study the algebraic things and vice versa. But yeah, so this concludes this part, and we might get some exercises on some of the details or related concepts. Okay, yeah, I'm done.